Hi, we are going to talk about projectile motion. Let's start with we need to talk about the independence of perpendicular motion, as in motion that is vertical and horizontal. So, um, this is a, schematic or recreation of this, but here is snapshots of the motion of balls, one that is just dropped from rest, and the other one that is launched with some velocity in the horizontal direction. And what this is showing us is that even though this yellow ball was given a horizontal velocity, that doesn't change the fact that its height is at the same point at every time instant. And so that's what this is showing, that even though um, blue ball in this case, was launched with horizontal velocity, its vertical velocity reacts or acts the same way as the ball that didn't have any horizontal velocity. So the point of this is to show that even if there is motion in Y or motion in X or vertical versus horizontal, um, that they don't affect each other. They happen independently. The thing that they affect is the motion of the overall motion of the object. So again, the projectile motion, actually, let's go to the next slide. Projectile motion is the motion of an object when it's given a initial velocity in the horizontal and vertical directions. It can also be an object falling that is given just horizontal velocity, like here. This one was just given horizontal velocity, but this makes a parabola, which defines projectile motion. So a parabola, like we see here, as the path of the motion is what defines projectile motion. R here is saying the range. We'll get to that. But the main feature of this motion is that most of the time, if there's velocity in both X and Y, it will be at a given angle. And we can look at the velocity vectors for the object at different points in its path. So start here. Initially, we're launched at this angle, and it looks like the angle is pretty big because the y component of the velocity is much larger. The vector is larger than the x component. So then we can start on the path, and we see, okay, in these first couple steps, the velocity in y is getting smaller. We can noticeably see that, but the velocity in x is the same. And it's even velocity in y is even smaller here. And then here, there is no velocity in y. It goes to 0. And then we get velocity in y in the opposite direction now. But the velocity in x is constant the whole time. And so what's happening here is projectile motion is showing us an example of a combination of horizontal motion with vertical free fall. So remember, vertical free fall was where the acceleration is just the acceleration due to gravity, and it's pointing down the entire time. So the y component of what's happening in the motion here is the same thing we saw with just free fall examples, where if we launch an object up with an initial velocity, the whole time acceleration due to gravity is pointing down. And so for a while, it's just decreasing the y velocity of our object, but then it gets to its maximum height, as high as it can go, and that's when the velocity is 0 temporarily. And then it changes direction and it starts falling instead of going up. And in that case, the acceleration and velocity are in the same direction, and so the velocity gets bigger as it heads back for the ground. So we see that same motion happening, but we have an added component. We've also given it some velocity in the horizontal direction. So that means instead of just going straight up and down, it goes straight up and down, but also goes in the horizontal direction. And also want to note, and this is something too that we talked about in class, but I only like kind of briefly mentioned it. Once you have kind of passed that peak height point, y max is sometimes what it's called, that point where the velocity in y is 0, all of the points at the same height in y are going to have the same magnitude of velocity. It'll be negative because again, it's going down now, but it'll have the same magnitude. So the place where this is different is if the object continues past the original starting point, the original starting height, I mean. So in that case, then it's going to get bigger and you don't have like a baseline to compare it to. But then we have kinematics equations to calculate. I also want to note, so the range, sometimes you're going to be asked for that, and I mentioned that on the previous slide. That just means the maximum distance in x horizontally, but it is only when the height is back at its initial position. So for example, like this one has laid it out at 0 since this is on the 0 line. So when it's back to 0, that is the range of the object. But if it was down here, it just works slightly differently, can work slightly differently, and we can still get the final position in x. So we talked about, we went back over vectors, or vectors, and this is part of play, because projectile motion usually launched with an initial velocity at an angle, and we want the x and y components of it, because, and kind of like, I mean, I guess I'll make it explicit now. We saw in that first slide that the perpendicular motion, horizontal and vertical motion, is independent of each other. But that means we can't mix up our variables when we're calculating them. So we have to distinguish the velocity in the x direction and the velocity in the y direction. And so that's what we're doing here. And so we have our initial velocity and our launch angle, and then the x and y components of it. And again, you can always put the y variable over here if having it shaped like a triangle helps you. That's totally fair. It can also be helpful to have it on the x and y axes too. So anyway, the x component is adjacent to the angle, so that's going to be cosine. And then that means that the y component is going to be sine. And this will be what it looks like for projectile motion, as long as the angle they give you is from the ground. If they give you like the angle from the vertical, then you have to think about it differently. And another thing with both or connecting the range or horizontal distance and the launch angle. So depending on the horizontal distance, the maximum horizontal distance of the object depends on the angle it's launched at. And we can see this here. This is just showing us the path for different launch angles. So let's start at the bottom with 15 degrees. It just doesn't go as far. 30 degrees, it goes pretty far. 45 degrees, it goes the farthest. So if you're asked about the maximum possible range, for example, and you're not given an angle, it's because the angle is 45 degrees, because that's what will give us the maximum horizontal distance. And then you can see that 75 degrees gets us back to the same distance as 15 degrees with a whole bunch of time spent in the air. Okay. Oh, and in these cases, the initial speed is the same. So this is just changing the launch angle, nothing else. And I just want to also point out that in projectile motion, because again, we're thinking about free fall acceleration, The acceleration in y is negative g. The acceleration in x, unless otherwise stated, is 0. So we're just going to assume there's no acceleration in x. Unless, again, it says otherwise. And then this is just a page you can refer back to, but usually the velocity in y will be the initial velocity times sine of the angle, and in x it'll be the initial velocity times cosine of the angle. So yeah, now we're gonna do a couple examples. Yeah. Okay, let's read the question. In the sport of dock jumping, dogs run at full speed off the end of a dock that sits a few feet above a pool of water. The winning dog is the one that lands farthest from the end of the dock. If the dog runs at 8.5 meters per second, a pretty typical speed for this event, straight off the end of the dock, that is 0.61 meters or 2 feet above the water, how far will the dog go before splashing down? So let's start by drawing our situation. And please excuse the drawing of a stick dog that I'm about to make. There we go. And it has a tail. Okay. So there's its velocity, and then we have the water, and the water is 0.61 meters below the dock. Okay. Now let's do our knowns and unknowns. We know. Well, actually, first of all, I want to point out something. Let's see. If the dog runs at 8.5 meters per second straight off the end of the dock, that is telling us that this is not launched at an angle. We just have horizontal velocity initially. So this initial velocity is just in x, and it is 8.5 meters per second. Don't worry, we'll do an example where we have both too. Okay, so that's one thing. And then we can say that we can take our initial position to be 0.61 meters, so that our final position is just 0. It doesn't have to be that way. You can always set your initial position to be 0, but this is kind of like a neat example where we can do it this way. So our initial position is 0.61 meters above the water, and then our final position is the water, which is 0 meters for us. And I guess we should also say that our initial velocity in y is 0. And then let's do our acceleration. Our acceleration in x is 0. Our acceleration in y is negative g. And then one other thing, which me writing a coordinate axis right there kind of does it, but we should explicitly say that the initial position in x is 0. Cool, let's do unknowns now. So what don't we know? Well, what are we asked for? How far the dog goes before splashing down. So that is the displacement in x, or the range. We also don't know the time interval of that, and we don't know the final velocities. Because when you're asked, and I'll probably say this again another time too, but when you're asked about the final velocity, you can't just assume that it's 0 because it hit the ground. Usually it's talking about just before it hits whatever, the ground or the water, what is the velocity? So anyway, that's just an important point. Okay, cool. Now let's look at our equations. Let's see. So x final equals x initial plus v initial x times the time interval. V final equals v initial plus acceleration times the time interval. Y final equals y initial plus v initial y delta t plus 1/2 a delta t squared. And finally, v final squared equals v initial squared plus 2a times the displacement in y. You may notice that I'm like, some of these are in x, some of them are in y. That's like, in general, there's no real distinct Reason why, other than I know that there's no acceleration in x. So I know that I can't use this top equation for y. And then I know that at least the other equations, important features are canceled out for x because the acceleration is 0. So that's where the labeling is coming in here. But let's take a look. Okay, we don't know this final position in x. We know the initial velocity in x, but we don't know the time interval. So that's kind of a problem because this is the only equation that really works for x, but we need that time interval. So let's look in at the next one and let's think about it for y. We don't know the final velocity. We know the initial velocity is 0. We know the acceleration, don't know the time interval. That one's not going to help us. Let's see. We know the final and initial positions for y. We know the initial velocity is 0. We don't know the time interval. We know the acceleration. And again, don't know the time interval. Okay, this one only has one thing we don't know. And let's look at this last one. Don't know the final velocity. We know the initial velocity. We know the acceleration and the displacement and y. So that one only has one thing we don't know too, but we're not asked for the final velocity. So I don't think we should find it if we're not asked for it. But what we can do is find the time interval from this long kinematics equation and then plug that in to this one. So let's do that. Let's write out that long kinematics equation. Y final equals y initial plus v initial y delta t plus 1/2 acceleration y delta t squared. Okay, let's cancel some stuff out, or at least say this equals 0. So y final equals 0. The initial y equals 0. So that eliminates some stuff. See, 0 equals y initial plus 1/2 acceleration and y delta t squared. And then we can just solve for the time interval. So let's subtract y initial on both sides. Negative y initial equals 1/2 acceleration in y delta t squared. And then let's divide 1/2 the acceleration in y on both sides. Negative y initial over 1/2 acceleration in y equals time interval squared. And then we just can take a square root of both sides and we have the time interval by itself. So square root of y initial negative y initial, and then I'm going to put g in here so that it's negative g. And so this is the time interval, and that way our negative signs cancel out, so we don't have to worry about them. And finally, we can just plug things in. So y initial is at 0.61 meters, and we have 1/2 and 9.8 meters per second squared. So this gives us a time interval of 0.35 seconds. So now we have enough information to answer the actual question given, which was what is the range or the final position in x. So let's do that. Let's see. X final equals x initial plus v initial delta t and v initial x. And right away, the initial position in x is 0. So this simplifies the equation to x final equals the velocity in x times the time interval. And this is the 8.5 meters per second times the 0.35 seconds. And this gives us rounding to 3 meters as the final position in x. That's how far that dog jumped from the dock. And there's some things I want to point out real quick before we move on to the next example is that a lot of the times in projectile motion, how the problems work is that for one thing, you need an equation in x and an equation in y to solve what you're looking for most of the time. And the common example is going to be you use the information you have in y to find the time interval and then use that to solve what you want in x. So just a heads up on that. Now let's do this other example. So we have a soccer player kicking a ball at an angle of 36 degrees from the horizontal with an initial speed of 15.5 meters per second. Assuming that the ball moves in a vertical plane, all it's saying there is you can ignore the side to side motion because the world is three-dimensional, so it might not just go in a plane. It might kind of go at an additional angle, but we're not dealing with that third dimension. So anyway, that's all that means. And then we want to find the time at which the ball reaches its highest point of its trajectory, its maximum height, the time of flight and the range, and then the velocity when it strikes the ground. So that's a lot of things, but that is on purpose because I wanted to give you this example problem because it does solve for a lot of things. So that way you have an example solving for a lot of things. So let's draw the situation. Here is the player kicking the ball at an angle of 36 degrees, and then it's going to do this projectile motion path, and then eventually it will land on the ground. And some of the stuff we're asked for the maximum height and the time to the maximum height. And we're asked for the range. I'll just call it the displacement in x, and the total time, which we'll just say is the time interval. And finally, we're asked for the final velocity, the final. Cool. Let's write knowns and unknowns. Actually, trying to decide. Yeah, it's fine. We'll write it. I was trying to decide because we have kind of different snapshots of time, trying to decide if we want to write the knowns for each of those, but we'll write the overall ones too. Okay, so we're going to define our initial position in x and y as 0 meters as our origin. And then our initial velocity, I'm going to give it the vector form so we know that it is not split up into x and y, meters per second at 36 degrees. And then the acceleration in y is negative g, negative. And acceleration x is 0. And then I guess we can also say that the final position in y is 0. At least eventually. It's not necessarily the final position for finding the maximum height. And then our unknowns. We don't know the time interval, we don't know the displacement, we don't know the final velocity, and we don't know the maximum, or the time to maximum height or the max. Okay, cool. So now before we like go through our equations and stuff, I want to look at the kind of specific points of the trajectory that we're looking at. So I'm going to combine A and B here because they both are talking about the same time. So they're asking us for the time to max height and then also what that max height is. And in this situation, there's slightly different things that we know. So, for example, okay, our initial position is still 0. And our initial velocity in y is the same, which, by the way, sorry, I didn't draw this yet for you. Let's do that really quick. Velocity 36 degrees, velocity initial. And then we can get the x and y components, the x component and the y component. And you can see because the angle is coming from the horizontal that y is going to be sine and x is going to be cosine. And just as a further reminder, this is coming from the definition of sine and cosine. So sine is the opposite over the adjacent. So in our case, the opposite of the angle is y, and then, sorry, not over the adjacent, over the hypotenuse. And that is the initial velocity. So all I'm doing to get these equations is multiplying that whole thing by the initial velocity to solve for the x and y components. Anyway, back to this. So our initial velocity is in y is the initial sine theta. And this is the maximum point of our trajectory. That is when the velocity in y is 0. So we will just call that v final for this time period, and that is 0. And then acceleration in y is negative g. And I think that might be all we need to know specifically for this. And you'll notice that I'm leaving out the x stuff because it doesn't really help us in looking at this. And then let's pull out those kinematics equations. I'm actually just gonna move this down and put them up here so then we can refer to them for each part of the problem. So x final equals x initial plus v x delta t. V final equals v initial plus a delta t. Y final equals y initial plus v initial y delta t plus 1/2 a y delta t squared. And finally, v final squared equals v initial squared plus 2 a y delta y. Now, okay, so now let's look at this. Let's see. We know the velocities and the acceleration, and we want the time interval, so we can definitely use that equation. Cool. And then we don't know the final position in y. That's what we're looking for. We know the initial velocity. We don't know the time interval, but that previous equation will give us the time interval. So this equation is a maybe for that. And then this last equation, v final, v initial, we know acceleration, and then we want the displacement. So we could solve this either by finding the time interval first and then plugging it into the long kinematics equation, or going straight to this second velocity equation. I think we will solve the two equations that I put the arrows next to. But again, there's multiple ways to solve these physics problems. So let's start with time, because that was what they asked for first anyway. A delta t. And let's solve for the time. So subtract the initial on both sides. Okay, so v final minus v initial equals a delta t, and then we just divide the acceleration on both sides to get the time interval by itself. V final minus v initial over acceleration equals delta t. And so v final, as we said, is 0. So 0 meters per second minus 15.5 meters per second sine of 36 degrees divided by negative 9.8 meters per second squared. So that's going to make our negative signs cancel, which is good because time is not negative. That's always a sign that something might have gone wrong, is if your time ends up negative. Okay, and this is 0.93 seconds. So that is the time to the maximum height is 0.93 seconds. Now let's find the maximum height. And again, we're going to use this equation this time. V final squared equals V initial squared plus 2 times the acceleration times the displacement in y. And we just solve for the displacement in y. Which actually is a good reason to have used the long kinematics equation, because then you don't have to rearrange it at all. Oh well. Oops, that's an eraser. V final squared minus V initial squared equals 2a delta y, and then we just divide everything by 2 times the acceleration. And you'll notice that these problems solve out similarly. And that makes sense because it's a similar situation and similar things we're looking for, similar equations. So you'll find that they look that way. Okay, 0 meters per second for V final minus 15.5 meters per second, sine of 36 degrees, that whole thing squared, divided by 2 times negative 9.8 meters per second squared. That way, again, our negative signs cancel out, and which is good because we wouldn't anticipate the maximum height being negative. And this gives us maximum height of something, 1 second, okay, 4.2 meters for maximum height. I guess we call that y max, not just displacement. 4.2 meters. So that is the answer to that part. Next up, we're asked for the time of flight, so the total time, and the range. And I guess I'm going to do that on the next page. Yeah. Pick a color. We'll go with purple. So actually, sorry, first, write out what we're doing. Displacement and total time. And let's write what we know. Okay, so x initial is 0, which is also y initial. Y final is also 0. Let's see. B initial, we're going to just do the vector form is 15.5 meters per second at 36 degrees. And from that, we can get the x and y components of the velocity. Acceleration in y is negative g. Acceleration in x is 0 meters per second squared. I think that is all the relevant information. So let's go back to the equations. Okay, we want x final. We know initial and we know the velocity. We don't know the time interval. So again, this is a point where we're going to need to solve for the time interval somewhere else. Let's see. We don't know. I guess I didn't put that we don't know the final velocity. And remember, I said you can't assume it's 0 just because it's hitting the ground. So we don't know that. We know the initial velocity for both. Know the acceleration, don't know the time interval. That equation is not helpful. We know the positions in y and the initial velocity in y. Don't know the time interval, know the acceleration, don't know the time interval. This equation could work to get us the time interval. And this one, we don't know the final velocity, know the initial, and we know both of these, but that doesn't help us. Okay, so it looks like 2 equations again. We have to find the time interval using the long kinematics equation and then plug it into the other equation. So let me pull those equations over. So we have y final equals y initial plus v initial y delta t plus 1/2 acceleration in y delta t squared. And then our other equation is x final equals x initial plus vx delta t. Okay. Now, let's set the things that are 0 equal to 0 in this long kinematics equation. So both of the positions in y are 0 because it starts on the ground and ends on the ground. And that's all we can do at that point. So 0 equals v initial y delta t plus 1/2 acceleration in y delta t squared. Now our system, our equation is equal to 0, and both terms are multiplied by the time interval. So we can actually cancel that out, or more formally, we can just divide everything by the time interval. Not the time interval squared, just the time interval. So that gives us 0 equals v initial y plus 1/2 acceleration in y times the time interval, no longer squared. And that just makes it easier and means we don't have to do quadratic formula. What am I doing? Okay, now let's solve for the time interval. V initial y subtracted on both sides gives us negative v initial y equals 1/2 acceleration in y times the time interval. And then we divide everything by 1/2 acceleration in y. And that gives us the time interval. Negative v initial y, 1/2 acceleration in y equals the time interval. And then the negative v initial, I'll write this as the full form of the velocity in y. And then we will write 1/2 negative g. I'm not going to plug in the numbers quite yet. But this way, our numbers cancel out. Because again, time is not negative. So what do we get here? We have 15.5 meters per second times sine of 36 degrees divided by 1/2 times 9.8 meters per second squared. So this gives us 1.86. You could round this more, but we're going to keep using it, and it helps not to round it too much. Right away anyway. Okay, now we have everything we need to solve the x equation. So let's do that. And I guess first we can say that the initial position is 0. So x final equals velocity in x times the time interval. So velocity in x is 15.5 meters per second times cosine of 36 degrees. And then we multiply that by 1.86 seconds. And this gives us a position of 23 meters for our final position in x. Nice. Okay, one last thing to get, and that's the final velocity. I did give you a hint about that in the lecture, but we're still gonna calculate it just to show. And sorry, this lecture is getting a little bit long. The final. So, what do we know? We know y initial equals 0, which is also equal to y final. Am I using? No, okay, I haven't used that color for that. X final we just found is 23 meters. We found the time interval of 1.86 seconds. And then I'm not going to write it again, but our accelerations and initial velocities are the same as before. Oh, but there is one more thing we know actually. Initial velocity in x is equal to the final velocity in x because there's no acceleration. So that is just going to be the initial cosine theta. So hey, we already have part of it. Let's go back here and see. Looks like we probably want to use this second equation because so we don't know the final velocity. That's what we want. We know the initial acceleration and time interval, so we can use that one. And potentially, no, that is the one we can use. Yeah. So let's pull in the equation. V final equals V initial plus A delta T. And then, let's see, 15.5 meters per second, sine of 36 degrees, minus 9.8 meters per second squared times 1.86 seconds. And this gives us, let's see, for velocity in y, negative 9.12 meters per second. So that's a velocity final in y. Velocity final in x is going to be that 15.5 meters per second cosine of 36 degrees. And that one is, oh, I don't have it there. Let's just check really fast. I think it's 12.5. Yeah, 12.5. 12.5 meters per second. So that's what, let's look at what this looks like. Velocity in x that way, velocity in y this way, and then we have our total final velocity and some angle. We'll say final angle. So to get the final velocity, it's just the square root of vx squared plus vy squared. And this is going to be 15.5 meters per second. The final. And the angle, this is where we use tangent. So tangent of the angle, also angle final, is opposite over adjacent. So vy over vx. And then we take the inverse tangent of both sides to get the angle. Tan inverse of vy over vx. So this is negative, or tan inverse of negative 9.12 meters per second divided by 12.5 meters per second. And this is going to give us an angle of negative 36 degrees. So this is the part where I was saying I hinted at it in the lecture. Um, the velocity is the same magnitude, opposite direction, because we're at the same height again. And one other thing I want to point out is if you find the time to maximum height and your final point is also at the same level as your starting point, then the total time interval is twice the time to maximum height. We can talk about that one more later on. Yeah, have a great day. Sorry the lecture ran long.